Hello, everyone. Welcome to the binary half of the podcast for this week. I'm Spectre. With me is Z. We'll cover the Spot the Vuln challenge solution for this week, and then we'll get into some of our news and exploits. So, Z, I'll let you take that away.
Yeah, this week's Spot the Vuln is a JavaScript one here. It's actually based off of, I should have gone and looked it up. We covered a little bit about prototype pollution in a prior episode. Effectively, that's what we've got here. On line 19, got that it's created the query object, just kind of your standard JavaScript object, couple empty braces for it. And then two user-controlled values are used as indexes into that, array, dictionary. They're used as keys. Therefore, set key 1 to __ proto __ or prototype, and you can start setting prototype values. Exactly how you'd exploit that depends on the actual application. All this would kind of cause is new objects being created will inherit those prototype values that you set. So if there's somewhere in the application that maybe renders as HTML if a certain attribute exists or is set to a certain value, that would normally either be left as undefined or something like that, you'd be able to trigger XSS that way. It really depends. I was going to include like an XSS in this challenge, but I figured it's simple enough to just keep it as the actual prototype pollution and leave exploitation for something else.
First time we've had a non-C based Spot the Vuln challenge in a little while. So,
It's only been a few weeks, I think. I think a few weeks ago we did the SQL injection one.
yeah. But prototype pollution is a bit of a weird one. You don't really see it too often. Like you said, we did cover it somewhat recently. But yeah, you don't see it as much as some of the other like bug classes that we see like every week on the podcast. So
I
yeah,
feel like it's a little bit harder of an issue just to detect when you're just kind of scanning through things. You don't always realize exactly how much control you can gain there. It does require, you need to understand the whole application to actually exploit it. So it requires that kind of deep knowledge of your target, which in a lot of web app testing, you're really not gaining. You're going through, you're testing all the inputs for whatever, not necessarily thinking about these aspects. Not necessarily even seeing, where this basically how all the data is flowing to actually notice this sort of setup. It's just it's not easy to find. If you're looking for it, like you're aware of it, you're looking directly for it, maybe it's easier. But just kind of left out on a normal test run, I feel like it's really easy to overlook.
it's not something you can easily just stumble upon. Yeah.
Yeah,
Um,
I mean, it's not like you can just place that single quote in and see it break, like
yeah.
with SQL injection.
That said, we did get some pretty quick solutions to it. I believe this challenge was solved again before the like yesterday's episode even went live in the Discord. So
Yeah, I
you know,
posted it kind of early in Discord, but yeah.
yeah, quick solutions.
All right. Well, moving on from that one, we do have our first vulnerability here, which is in the Gerbv, either library or more of an application, but used on these. I should have looked up exactly how this is used, but this is kind of just one of those parser issues. Talk about this,
So
especially. Go ahead.
I was just gonna cut in and say like this is on Gerber files, which is used for describing PCB layers. So it's kind of funny because you'll see some stuff in this issue where it talks about like drill parts and stuff like that, and it seems like something you wouldn't expect to find in like a parser application, but that's because it's parsing schematics and it's actually used for like drilling PCBs and stuff.
Well,
So
yeah, I was thinking it was kind of
it's a
like
really weird like area.
a CNC sort of milling drill type idea there. That's kind of the idea I got from it and how it was being used. Um, that said, that's very much, not my area of expertise. So, um, it's a parser issue though. They do treat this as when it comes down to their CVSS score, they gave it a nice high 10. Calling this one, network accessible because of the fact that some Some places where they use the PCB as an example will let you upload the file, therefore kind of giving a networked attacker access to just provide a specially crafted file and gain code execution. Most of this is background on how you're actually reaching the code node structure of the file, all of that. All it comes down is this T code where there's a line starting with the letter T. Next thing it gets is a number, the tool number that it's going to use. Reads that out from the user and uses that, or checks that number against the tool min and max values, and then uses it as an index into an array. The problem being, although it does the check on where's the line here? On one of the lines where it checks the min and max, does that check, all it does is prints a error message saying, hey, this number is, invalid. But it continues just fine. So you get an out of bounds, ultimately leading to an out of bounds read and out of bounds write, based off the number you provide it, just on an index into that tool. I guess aperture and then tool number. You can see the access here. You're able to influence the write. It's not a direct value copy. It'll divide it. So it's a floating point value. It'll divide it by either 24 or by 1,000, depending on the units. But beyond that, so a fair degree of control from the user, arbitrary write. On that, I mean, straightforward issue. Like a lot of the Talos posts, there's a lot of background here in terms of like actually reaching that code and working your way through it, but it's just, your standard parser issue.
Just as a comment on that, because funnily enough, in the reverse engineering Discord, we had kind of a discussion about this recently. With Talos, it's either you get a bunch of background information that explains the bug, or you get like a crash with nothing else. It's like figured
That's
out.
true. Yeah.
It's a bit varied with Talos. You don't really get an in between though. It's either like a bunch of information or no information. But
Yeah, I mean, we don't tend to cover the ones with no information, but I definitely see those when I'm going through the topics that we might cover.
yeah. So basically, like the problem here is is useless error check. If you're just doing a quick skim of the code and you'll see that error check, it's easy to go, okay, it's fine, it's handled here, but it doesn't actually really do anything. It's just printing to the log.
I mean, there's like no reason for them to not actually air out there.
It's weird, I agree. Because in like we've seen some of these types of issues before, and we've kind of been charitable with saying like, okay, an error here is really difficult to handle. It's very deep in the call stack, and you would have to unwind a lot and whatever. But here, yeah, I can't really think of why they don't error out here. It's a little strange. It almost seems like they were writing the code and they just wanted to be aware if that was a possibility when debugging or something, but then they just never did anything to handle it. So
Yeah, I mean, it's just also because like even if they weren't going to handle it, like continuing on is not a valid answer.
no. So yeah, basically they do this table lookup, and you can provide a bad index in there, so you can get an out of bounds read on the tool table. They do use that to get corruption later on. If the aperture pointer that they read with the out of bounds access turns out to be a null pointer, it'll allocate and set up a new aperture using the size that the user can influence, and that creates an out of bounds write situation on that size field. They speculate how this could be used in exploitation, which is a little interesting because a lot of the times Talos just kind of stops at the bug. They don't really talk about the exploitation much. But here they propose is like something you could do is maybe smashing the next field of a linked list that's used in the stats object, which is adjacent to the image object where this original out of bounds access happens. And you can use that to insert a pointer and create a dangling pointer when that list eventually gets iterated and destroyed to get an arbitrary free. They don't really go much beyond that though. They just kind of leave that as like a possible attack vector and then leave it at that. But like I said, that's kind of interesting because that's farther than I've seen a lot of Talos reports go on the exploitation side. And like, yeah, a totally valid attack strategy. Attacking a linked list like that to get a use after free situation. And again, just kind of illustrates something that I hammer on a lot with like, you start off with an out of bounds read on the table, which isn't immediately very useful. But you use that to then get an out of bounds right, which you then use in their speculation to get an use after free or an arbitrary free.
Well, I mean,
And
they don't
then yeah,
really, um, when it comes to transitioning from the read to the write, I mean, I get where you're coming from in describing it as like using that to get the write, but I mean, the write really just happens as it keeps processing, gets that letter C and then reads another number. Like, it's basically the next thing it's expecting to parse out of the line. Like, they're not
kind
really
of.
like
I mean, you do need to get the null appert pointer, which is kind of where I was coming from with like escalating the primitive a little bit. You do have to do a bit of effort. I mean, you could just
fair. I
stumble on it
mean,
being a null pointer, but yeah, I mean, I kind of see what you're saying too.
yeah,
It is
no,
kind of a
that's
given, but
it's fair. Yeah, I kind of see that as a natural extension still of it rather than extending, but I mean, that doesn't matter.
yeah. The idea there being though that you're kind of chaining your issue to get better and better stages of corruption, right? So this is yet another example of that. An example like probably like 1,000 on this podcast through its lifetime. But yeah, that's something I like to talk about. Whenever I see it crop up. Yeah, overall, this is just a really interesting target, I think. The bug isn't super interesting. It's just like an unrestricted size or an unrestricted index getting through. Um, but I don't know if we've ever really seen an issue in this type of application where it's doing like CNCing and stuff. It was kind of interesting to think about, I guess. It's not super relevant for the vulnerability and exploiting it, but just
Well, there
the
was one of the other Talos reports. It wasn't like CNC, it wasn't a drill, but I think it was another hardware thing. Um, Maybe a 3D printer that we've covered.
oh, you might be right. That might have been a long while ago though, because I don't remember anything like that recently. But
Yeah, I don't
it
recall
is
how
kind of
long
ringing a
ago it
bell.
was, but I do recall another Talos issue where it was another kind of parser issue. That time dealing with getting access on the 3D printer, where again they kind of made that argument about people being able to upload files and get them parsed, and thus having that network attack surface. And that is definitely a valid attack surface that is probably not looked at a ton.
Yeah, I mean Talos does research on a ton of different targets. They've got more diversity in the targets that they look at than I think like a lot of the other common companies that we cover. So
Yeah,
yeah,
I
you
kind
never
of
know
feel
what you'll
like a
get at
little.
Talos.
Yeah, I mean, a little bit that, like, with some of the other companies we cover, they're looking at some of the big, high-paying targets.
Hmm.
I doubt there's even a bounty on this one.
Yeah, although Talos does look at those too. Like they have reported browser bugs and stuff before too. So
True, true.
yeah. So Realize put out an article on some vulnerabilities they found in Samsung TVs and their tzdemuxerservice, trusted app that runs on TrustZone, which we don't see very often. As the author points out, it's very rare for trusted applications to be open source, and in general, it's just kind of a tough area to target for vuln research. Um, but in this case, the trusted app used by Samsung here is licensed against the LGPL and as such is open source. And they found some vulnerabilities in it and their memes. Before covering the issue, though, I do quickly want to talk about the architecture of like the application and how TrustZone is being used here for those who might not be familiar. So basically, in a setup where TrustZone is used, you have two different worlds, as they're called. You have secure world, which is where trusted applications and a trusted kernel runs, and the non-secure world, which is where non-trusted apps and non-trusted kernel runs. Um, and so, as you can imagine, more sensitive actions like crypto or whatever is usually, if TrustZone is being used, it's going to be put into a trusted application. And the secure world app exposes an interface that the non-secure world can call into, feed inputs, and get whatever output they need. And a trusted app can define various handlers or entry points, notably a command entry point. And that's where the issue comes into play here is this tzdemuxerservice exposes a command entry point that implements a bunch of different commands, like like initting clients, submitting and dumping normal data, video packets, codec information. Since it's a media demuxer, they're doing a lot. They have a lot of commands exposed here. As to why they have this in TrustZone, it does seem a little bit weird to me. I'll be honest. I can't really think of like what reasoning they might have for putting that in TrustZone, but doesn't really matter. The fact is, it's there. And in multiple of those command
I mean,
handlers,
my guess is DRM.
possibly, but yeah, I guess that would make sense to have like the decoding and everything happening where you could have the DRM enforced and trusted world. Yeah, fair point. So yeah, guess that makes sense. But yeah, the problem is in multiple of the command handlers there, they take a pointer from non-secure world and they just operate on it directly. They don't do any checks to ensure that the pointer actually points to non-secure world memory. So you can just pass a pointer to trusted app memory and it'll accept it and perform whatever operation it goes to do, like a write or whatever on it.
Yeah, and I
Kind
mean,
of a
I
meme.
wasn't aware of this when it came to passing him over, but the way they end up fixing this, and this fixing it, 5 of the 6 vulnerabilities, it's the same fix. All they did was Samsung indicate to us that param0 parameter is now verified to be this t param type memref inout, which is, as Spectre just said, making sure that it's pointing to that user side memory. That's it. I didn't realize that they actually indicated on these different types of the parameters being passed through, like as it's coming through this call into the trusted environment, that it's actually kind of typing them in this sort of pseudo way. I just wasn't aware of that and being able to pass because what they expect is either passing things in is by reference or by value. They make mention of that also as kind of being the expectation. They just don't check whether or not it is a reference or a value. Therefore, pass it in. It's going to treat it as the reference because that's what it's expecting. Oh, but obviously you pass it in as a value and it just takes that value as the pointer anyhow. I did just find that an interesting aspect of trusted execution calling into it, just because I wasn't aware of that. And we've only covered, I think, maybe 2 or 3 other trusted applications before on the podcast. So learning things from this.
Yeah, and I think even then, at least one of those times was in the context of like a research paper that was. It wasn't like a specific bug. It was more just looking at like what can be found or whatever.
I
Um,
think, and one of the times was also realize another one of their blog posts.
yeah. So this is a pretty funny bug because like they're using TrustZone here. Obviously, they are expecting some kind of boundary and they want trusted actions to happen in their trusted application. But then they're just completely like taking these unverified pointers and not doing any checking on them. It's like it almost seems antithetical to their setup to have a bug like this in place. But I mean, it's Samsung, it's TVs, so it's not that much of a surprise, I guess. IoT is uh, these kinds of issues are pretty common there, but yeah, it's just gave me a bit of a chuckle when I was reading through this. I was like, oh wow, because when you see TrustZone, you expect the bug to be somewhat like complicated and convoluted, but no. And this
Given
is
what I've
just they
seen
take a
of
pointer
Trust
and don't do
Zone,
anything on it.
I actually don't really expect that anymore. Given what I've seen of so many applications here, I think that it feels like a lot of the security is just coming from the fact they're black box, don't often release code, and it's hard to get that access to even like debug a trust zone application or have any degree of access to do any testing on it, and figure anything out. And it feels like a lot of their security just comes from the fact that they're hiding behind that black box and not because there's actually a deep requirement of like secure code.
In a lot of cases, TrustZone almost seems like security theater. It feels secure to use it. It sounds really scary, TrustZone, and it's enforced by the hardware and everything. But like, if you don't implement it correctly, then none of it matters. So yeah, like you said, I think it is a lot. A big part of it is the security through obscurity, by keeping those trusted applications, from being open source and whatever. And it's just maybe not an area that a ton of people are looking at too much. But yeah, a lot of the times that I've seen TrustZone mentioned in the context of a write up or a conference presentation, it's like, oh wow, this is a real like this is like a 2000 bug or something. This isn't complex at all, really.
So out of
But
chat, Taniwa3 mentioned. I'm surprised TrustZone itself doesn't check whether the memory is in trusted zone or not. And that's actually what I was just talking about, this T param type. When it's this memref in out, it will be validating that it's pointing to like the user memory and it's correct. The problem is that the application didn't check the type of the parameter to ensure that the pointer it was going to use was a memory. So if you pass it into it as a value, or that's how it seemed when they're kind of explaining it, they pass it in as they wouldn't pass it in as this type. Basically, they would pass it as just a value, but it would use it as the pointer.
Yeah, the obligation is on the application to check the type, which, being a bit charitable to Samsung, maybe they weren't fully aware of that. Maybe they just expected that to be like centralized, higher up and like in the communication between non-secure world and secure world that TrustZone handles. But I'm guessing it's like this, and the obligation is on the application to allow like flexibility for what applications want to do or whatever. So yeah, maybe it was just a misunderstanding of who had what responsibility when it comes to trusted applications. I could totally see that.
Uh,
So
I I can't, but sure.
fair
No,
enough.
on that one, like because it's just passing that information. They wouldn't have needed to define it anywhere and see to say this is this type of pointer or whatever. At least as far as well, maybe I'm wrong by that. I don't know, but it yeah, I mean it's pure speculation, and I don't know what people were thinking.
Yeah. So this issue existed in 5 different spots. It was in the command for client dump normal data, client dump video packet, get packet, get video codec info, and get audio codec info. So pretty much anything where it's dumping some kind of data, this issue exists. There was also a sixth vulnerability they detailed that was a little bit different. The vulnerability for that was basically that some areas would call malloc, but they wouldn't actually check its return value to ensure that it succeeded. Instead, they just went on to use it for operations like memcopy, which is a null deref. They point out it is possible that null could be mapped within the trusted application's memory space, which I thought was a little interesting because for the most part, in most applications, null derefs are pretty much dead in terms of exploitation. But when you're talking about TrustZone and these other more weird areas, I guess it's not too surprising. I guess that null could be mapped in the context of a trusted app, but yeah,
Yeah, and I'm not sure if it can. They're talking about as though it can, so I'd assume so. And makes sense with the trust environment just being a bit more restricted, both in terms of memory, in terms of power, basically in every sense. Kind of makes sense they might not run those same protections by blocking off that memory. So definitely feasible. They didn't show any cases of it actually. Like, I don't think they talk about any actual exploitation with it, just it uses the buffer, and that's all.
yeah. And Taniwa put something in chat that kind of succinctly wraps up like the what we were talking about earlier with TrustZone. And he says, I don't think it's security by obscurity, but rather poorly defined or misunderstood spec. TrustZone results in encrypted memory where the CPU holds the keys, but you got to use it properly. Like, yeah, that's basically what it is. Like, it's so easy to look at TrustZone and just be like, I am safe. I'm running in secure world, non-secure world, can't touch my memory, I'm fine. But if you don't implement it properly, then you're still going to be open to issues.
And
So that's
touching
what I was kind
on,
of alleviating to earlier with like the security theater aspect. Like it almost feels like it's hurting your security a little bit by putting so much trust into TrustZone to keep you safe without understanding the nuances of it.
yeah, I mean, both things are at play here. When I first brought up the security by obscurity, like what I was getting at was just the general idea of trust zone being secure or not, and needing. I think you had made the comment about needing difficult exploits for it at that point. I was kind of taking it as, Trust Zone feels a lot like it's just obscure. It's just hard to get any debugging access to it. Therefore, that adds the difficulty. But like this specific issue, it's open, is just, it's maybe not understanding the spec as was as you were just mentioning. Like, that's there also, needing to understand how to use TrustZone, that's also an aspect. But when it comes to the exploitation or finding vulnerabilities, I think a lot of the difficulty isn't actually in the fact they're writing good code. It's in the fact that it's just so difficult to get access. And like there's such a barrier to entry.
That actually reminds me of a topic that we covered a little while ago, and I totally forgot about it until you mentioned the like debuggability aspect and stuff. Um, I wish I had the episode on hand, but since I just thought of it, I don't. But we covered a topic before that talked about pulling like trusted applications and then emulating that in non-trusted userland to do like fuzzing on it and stuff like that. Um, but yeah, unfortunately, I don't remember exactly what topic that was on. But yeah, there's been some research into tackling that exact problem with trying to pull trusted app code into like a more easy to handle context for doing vuln research and automated testing and stuff.
Yeah, I think that was the paper that you were thinking of where we've covered it. But yeah, I don't recall.
I
That
think it
would have
might have
been a
been.
long time ago too.
Yeah. Um but yeah, they don't really go too much into the exploitation details here. It would be tough, I think, to do because, like you're saying, like TrustZone and trusted apps are kind of a black box. I don't know if you could exploit these issues on their own. Uh, like my idea with that is you would need some information on the memory layout, right? Like being able to take a pointer and do like a restricted write on it is great, but you need to know where to write to, right? So you might need like an info leak to chain with this as well. Um, that said, I can't say definitively
And what to
because
write.
it's and what to write. Yeah, exactly. But yeah, it's kind of specific to the application and what you do and don't have access to, and obviously that's pretty out of scope of the article. Um, so yeah, I think it would be a bit difficult to exploit, but still a pretty trivial bug in terms of the VR aspect. All right, so up next we have a Linux kernel bug in TIPC from Sentinel Labs, which is pretty significant because TIPC, or the Transparent Interprocess Communication Module, is common amongst all major Linux distributions, and it can be exploited locally without privileges or even remotely in some cases, depending on how the target might be set up. This bug was found through CodeQL assisted manual review, though the query wasn't originally written with the goal of finding an overflow directly. It was kind of meant as just a starting point for doing further queries. The query is posted in the article here. Basically, all it's doing is checking for any kmalloc calls and checks if the type for the size is 16-bit size, with the idea in mind that a 16-bit size would be easier to overflow than like a 32-bit or a 64-bit size.
Yeah,
Um,
thanks, Belika, for the sub.
oh yeah, awesome! 10 months. Welcome in. So yeah, like one of the results of that query was TIPC's crypto key receive function, which takes a received packet and parses it for key data. One of the things it parses from the packet is the key length for the provided key. So basically, like visualizing the packet, it has like the standard header um, where it has the name is passed of a fixed size, then it has the key length, then it has the auxiliary data buffer for the key itself. The weird thing is the key length provided from the packet isn't validated until after it's already been used to memcopy the key data into the newly allocated skey buffer. So there's validation, but it's completely pointless at stopping memory corruption because it happens too late. It's very weird code. So anyway, that allowed a heap overflow. It's also a pretty ideal one because you control the size of the allocation and thus can influence what kmalloc cache you have corruption in. And that's because the allocation size is based on the size of the message header. You also have control of the overflowed data because while the allocated size uses the message size is only validated to be in bounds of the received packet. So you could send a really large packet that's larger than what the message size is and get that data in the packet written out of bounds with the data you control. So it's a very ideal exploit situation. Though they don't really elaborate on that. After explaining the bug, they just talk about like what the fix was, which was basically moving the bounds check up before doing any copying. And I think they do some additional like checks in there too. But um, yeah, like this is one of the most ideal exploit situations you can have in the kernel. You can absolutely take this to like code execution. No question about that. So Yeah, kind of a surprising bug. Um, I guess just one of those areas that just hasn't really been looked at or hammered that much because, I mean, yeah, any code review of this area could have pretty easily caught this issue. I think, um, having the sanitization check or like just
Well, I
having that check so
don't.
late.
I'm not sure the having the check so late. The thing is that check isn't exactly a security check. It's having to stand in like that. But the key thing that that check is actually looking for is just if the size is the key size. Um, like as a check, it's not technically like it's acting kind of as a bound check because it's looking for a specific size value, but it's not really a boundary check. Like anybody reading that, I mean, if they're going for security, probably going to be a bit more aware of that. But in general, like you're reading that just as a sanity check on is this the right size, not necessarily a boundary. If that kind of makes sense. Like I could read this a little bit differently, basically.
Yeah, so Balika asked, how does this bug how did it get introduced? What's the Git history? I was just trying to do a quick search to see if I could get that for you because they don't elaborate on that in the article. They do mention that the bug is only exploitable or the bug was introduced in like 5.10 release candidate 1, and it was fixed in 5.15. So it is a pretty brief window of when this bug was in the kernel. It was only in there for uh, under a year. Um, that said, I did want to see if I could quickly find the Git commit that introduced the bug, but there's a few code changes here, and I think it would take me a few minutes, so I don't really want to do that like live on the episode. But afterwards, like in the Discord, I'd be down to like talk about that and do some further digging because yeah, that's a good question. Because obviously, this bug hasn't been in there forever, so there has been some code movement in TIPC. So
Yeah,
I'd
I
be
mean
kind of interested in that too.
it's definitely within a fairly recent time period. Like 510 I think was late 2020. Yeah, I think it was late 2020. I want to say like December or so. Cuz I yeah, probably December or so, and then 515 is pretty new. Um like it's the most recent. I'm not sure if 16 is out yet. I don't think so. I think 15 was this month's one. So I mean, the bug would have had to just be around for like a year.
Yeah.
So don't know about exactly how it was introduced, but just judging from the time frame, like being relatively recent, kind of makes sense that it's being disclosed now and wasn't necessarily found much earlier. Do we actually have a timeline in here on when they found it versus when it's getting patched? Because it probably just got patched with here at the end. I just found it in October. So yeah, there is a bit of a gap there, like at least that 10-month gap where it was in there without having even been reported.
Yeah. So like I said, I'd be down to like do some digging and talk in the Discord about that after. But I think it would take me a bit too long to try to do live on the podcast. That said, we do have another Linux kernel bug. Um, last for exploits, we have a Linux kernel bug from a listener actually and someone in the community, Telford Williams. This was a bug discovered in AMD's GPU driver through debugfs, specifically for configuration of DisplayPort test patterns, I believe. And that bug was in parse write buffer into params, which is called in the dpfi test pattern debugfs write handler. Basically, they allocate a write buffer array with kcalloc in the debugfs write handler that allocates a 100 byte buffer. But then in this parse write buffer into params function, they take the direct size passed in like from user side to copy in the data, and they don't bounds check that against the size of the allocation. So you have another trivial overflow. Since the allocated buffer is 100 bytes, the overflow is in the kmalloc 128 cache, which is a fairly decent cache to hit. It's not as active as some of the smaller caches like kmalloc 32 and 64, so you don't have a bunch of noise there. And it's kind of a good mid-range cache where there's a good amount of candidate objects to choose from for doing corruption. He then goes into detail on how he exploited the bug, bypassing modern mitigations like ASLR and SMAP and SMEP. He exploits the bug once after setting up a message object, which is in that kmalloc 128 cache, to be adjacent to the overflow object, and smashes the message type and message text size to get an info leak through out of bounds read. There, the info leak was responsible for getting the pointer to the mod probe path object. He then uses the overflow again to attack the SLUB allocator and smash the free list to create a dangling pointer and essentially get an arbitrary write, which is then used to smash the mod probe path data or object that was leaked earlier. This is a somewhat documented technique. The background there is Linux has this component called modprobe, which is used for adding and removing Linux kernel modules. Anyone who's done some driver hacking will probably be familiar with it. And the kernel contains this modprobe path variable in the kernel to know like what program to execute when it needs to call modprobe. And this path is stored in read-write data. So if you can leak the location of modprobe path and use something like an arbitrary write, you can use it to get the kernel to execute a path that you control as root. So yeah, I mean, cool and powerful exploit. Bug is fairly trivial, which, I mean, it isn't really surprising because we are talking about GPU code. Linux GPU drivers are just terribly bad. Well, let me walk that back a bit. GPU drivers in general are just terribly bad. So, I mean, it's not too surprising to see kind of a straightforward overflow with just no size checking in an area of code like this. There are a few things worth noting with this bug, though. Some circumstances. For one, you'd need debugfs to be enabled and accessible to an attacker, as the author points out in the introduction, which usually like that will be privileged off or it won't be accessible to like super unprivileged contexts. For another, if free list hardening is enabled, this exploit strategy will fail because free list hardening basically XORs the free list with a random key. So that's not to say that this bug wouldn't be exploitable in that case. You could totally exploit it in a different way, but this specific strategy of using the free list to get an arbitrary write, that wouldn't work if the free list hardening was enabled. But yeah, I mean, overall, still a great find. For those curious on the version information, the bug was introduced in 5.8 release candidate. I think it was RC1, but I can't remember for sure. Actually, no, sorry, it was RC2. I just found it there. So yeah, it was introduced in 5.8 RC2 and it was fixed in 5.14.15. So it didn't exist for too long, and AMD did get around to fixing it quickly. But I just wanted to point that out, to be fair, since, like I said earlier, the GPU code is terrible, and it still is, but at least they did fix it somewhat promptly. But yeah, I mean, just another Linux kernel heap overflow due to, bad checks or no checks in this case. And yeah, I mean, this bug and the last bug could probably be exploited in like the same way. It's a very similar situation, actually.
You kind of made this throwaway comment there about, the bug wasn't there for too long. I mean, how long is really too long for a bug to be sticking around for in the kernel? I mean, sure, it's definitely not one of those bugs that's been there for like 10 years. Like, 6 months, a year. This, I mean, just looking at the version numbers, probably about a year, a little bit more. Feels like a pretty decent lifetime.
So
Obviously, we're still going to find older stuff. There's so many variables involved with that too. Like, there's no absolute value. But yeah, what are your thoughts?
So when you're talking about version history for something like the Linux kernel, it's kind of unique as far as using the version as a reference point, because with the Linux kernel, people aren't really updating it between like major or minor versions super often. Often you'll have like a distro that just, its long-term support will use a set kernel version and it'll just use patch versions for security fixes, but it won't really change between, like, I don't know, 4.19 or something to like 5.6 overnight. Like, it's just not really going to happen. So the version compatibility when it comes to bugs is tricky to say whether or not it's been in there a long time. I think on a newer kernel, like here it's in 5.8 it was introduced in. Like, I don't think there's a lot of systems that are running 5.8. That's a pretty new kernel. So the fact that it was fixed before a lot of systems will probably be even updating to like a higher version. That's why I was saying like I would kind of agree with the sentiment that it wasn't in there for too long. As opposed to, if you had a bug that was introduced in like kernel version 3.9 or something and it's still present and exploitable in 5.8, that would be insane, right? That would be an insane bug lifetime. But here, where it's kind of in that development window where there's probably not a lot of machines in production that are going to be using the version in that range where the bug is like useful.
Well, so it is
That's where
worth
it's like,
maybe noting that I think it's 5.10 was the last LTS release. Um
yeah, I was just trying to see the long term support releases. Actually, I was
yeah,
trying to
so
get a
5.10 was the long-term support. So I mean this was in there long enough to hit the LTS window.
Yep, that's a fair point. Yeah, so 5.0, 5.4, and 5.10 were the long term releases. It seems for like the is that correct? Let me just
I
double
don't
check
know if
that.
5 well, 5.4 definitely was.
I'm just looking at this table and it kind of sucks because it's hard for me to actually. Uh,
Yeah, I mean 5 so what version did he say? 5.0, 5.4 and 10?
yeah,
Yeah.
yeah. So 5.4 was the 20th LTS release, 5.10 was the 21st, and 5.15 is the 22nd. So yeah, so usually it's every like, well, in the last in like Linux 5, it's been like every 5 minor versions there's a long-term support release. So yeah, I mean that's fair to point out. It would have been caught in the 5.10 LTS. Um, but yeah, still, I mean, with this bug, I would still say it's a relatively short bug lifetime. Just because when you're talking about the Linux kernel, um, there's quite a few different bugs that have been discovered that have been in there for years. So in terms
I
of
mean it's an old
scale,
code base for sure.
yeah,
No,
in
I
terms of
just thought it
scale, I
was
would say years is a long time. Under a year, it's fairly, you know, it's not as big of a deal, in my opinion.
yeah, I mean it's great one that it's getting patched here in within I'm going to say roughly that year. I'm just making a guess on that. I think it's a little bit more than a year. Um from introduction, not actually being reported, but just introduction to fix. I that feels all right. I mean, obviously, you'd want to catch it beforehand, especially something like this does feel like something, static analysis should have been able to pull out.
Yeah, another one of those bugs where like a code review would have caught it pretty quickly. It's
Or
it's
should
not a
have,
it's not a
yeah.
subtle bug. Yeah. But yeah, I mean, yeah, like I said, trivial bug. I mean, both the kernel bugs we covered today were somewhat trivial. The exploit, like the detailing on the exploit strategy here, though, is I think where the like value add is. And like I said, I think you could probably backport, so to speak, that exploit strategy into the other bug that we covered as well. So yeah, I mean that's what I think is really cool about the write up is just talking about how it could be exploited, um, detailing that free list trick a little bit, and yeah, like it's somebody from the community too, so we did want to shout them out on that. So yeah. With that said, we'll move into our last topic here, which is a research paper on a tool called Rudra for finding memory safety issues in Rust programs, which, as you can guess, if you're familiar with Rust and or some of the discussions we've had about Rust before, it tunnels in on unsafe because outside of unsafe, it's kind of difficult to have memory safety issues because that's like Rust's main offering.
And
So
it offers
yeah,
several guarantees regarding, safety and undefined behavior.
yeah,
So
that's
yeah,
Rust's
it's
entire like purpose. So it'd be pretty bad if it didn't involve unsafe, I guess. Um,
although in fairness, like there's a lot of unsafe code. The nice thing there is the fact that Rust um indicates that this is the unsafe code, and that is where you can put like your focus on. Like there is kind of that benefit of having it called out, but there is a lot of unsafe code. Like most applications are going to call into some code that's using unsafe at some point.
Yeah,
It's basically just going to happen.
basically Rust offers like attack surface reduction at a language level. Most of your code that doesn't need to be touching like raw memory or anything, um, you can have the memory safety guarantees, and then the rare circumstances where you need to like not be bogged down by those safety guarantees is where you can use unsafe. So yeah, it's very useful for that. So the basis for their tool here is like what kinds of bad assumptions or poor implementations can be found when it comes to unsafe code that can lead to memory safety issues. I'm simplifying it down a lot there, but that's the overarching summary of what's going on here.
Well, it's
But
that,
we
and
will get
obviously
into some of the patterns.
this is a tool that's trying to find those at what they're saying as ecosystem scale, basically, scanning everything for these sorts of vulnerabilities. I I'm not going to cover the real details on how they built the tool and exactly how they're scanning for these vulnerabilities. What I found more interesting here is just, the types of vulnerabilities that they are looking for and have found in Rust applications that do introduce memory safety issues. Because I mean, a lot of times we talk about Rust as, the silver bullet. Obviously, we've said several times on the podcast that there's still going to be vulnerabilities. It doesn't eliminate them, but it does kind of change how you're looking for them. So in this case, they kind of end up focusing on three very high sort of classes of issues or ways in which vulnerabilities can be introduced. And those three, as they term them, is panic safety, higher order safety invariants, and propagating send sync in generic types. Going through each of those, and I'll say this: they go into some of the implementation detail in the paper, so you can give it a read if you care about that aspect. They also have examples of where they found all these bugs in sample code. So if you want to actually do some like Rust code review or get some samples for that, you can kind of see a few examples here laid out. So it is nice for that. But with these three issues, panic safety is basically just with Rust, you panic, it'll unwind the stack and it'll start destroying all or releasing all the resources as it unwinds. Um, the problem being when you panic inside of unsafe code, a lot of unsafe code will violate some of the assumptions that might be made. So the idea being that inside unsafe code, you might bypass the Rust ownership system and extend lifetime, or you might create like an uninitialized variable. I think it's one of the cases they found where you temporarily just create this uninitialized variable, or said this object that bypasses the lifetime system, and you're going to clean it up before you return from unsafe, to return to the safe state. But for that slight period, you do that. So if you get a panic in that slight period where things are, as you might say, unstable, in that situation, as it unwinds, you can end up having that unwinding actually, say utilize this uninitialized variable as an example. So you can have uninitialized issues there. You can get a double freeze out of it, and that sort of issue just by panicking at just the right moment in that unsafe code. Oh, which frankly I wasn't aware of that as the sort of issue. I mean, obviously panicking, getting errors anywhere unexpected creates issues. It's just nice having these laid out. At least for me, I'm definitely interested in something specific Heap that, or sorry, something specific Rust things. Moving on to the second one here, the higher order safety invariant. This feels a little bit like a catch-all because they're kind of just talking about these common mistakes that might happen in the unsafe code. So with safe code, Rust is basically guaranteeing that you're not doing any of these sort of undefined actions. Your code has to work on every input that it says it allowed to work with. Like if it accepts this type, it has to be able to work with everything of that type. Um, or it has to enforce the checks. It can't just crash. So they use examples of, or the points of logical consistency, purity, and semantic restrictions. Those points just being like logical consistency. They use the example of total ordering, which clarified kind of what they meant for me. In C++, sort function where you kind of do a sort to give that callback function. In C++, your program can crash if that sort function kind of behaves somewhat illogically. and doesn't always treat like two particular values maybe are not always less than or always equal to each other. Like they don't always have that same association. If the function does that in Rust, though, that unsafe code has to make all of those checks. It can't it can't crash. It can't introduce sample states. Can't assume it's going to behave in some proper way. Similar with purity being just like if it tracks some state externally. If it's an impure function, if it writes out, if it does something, basically, if you give it one set of inputs, you've got to get the same value back. These are just assumptions that the developer in unsafe code might make. They're not actually like Rust specific. It's just you're in unsafe code. This is the sort of thing you need to be thinking about because Rust has higher standards for what you're writing. And then the third one was probably the more complex or most complex of the issues to get your head around, especially if you're not super familiar with Rust. That being the propagating send, sync, and generic types. So send and sync are kind of the two traits um, that govern thread safety. If something can be sent, if it has that send trait, it's used to indicate that type can be sent off to other threads, thread safety. Sync, it can be referenced by multiple threads, again, dealing with thread safety. And, if a type has that, it's safe. It's got to be safe for all the use cases, cross thread. The problem comes in, so if an object or if a type if all of the types that make up the type have that, then it's going to inherit the send or sync traits. Otherwise, you've got to manually implement that. And that's where you can start having issues. So if you manually implement the send and sync traits, as the objects say get expanded, somebody might not be aware of that manual implementation, and thus it can kind of just fall into the cracks. Or with the propagating aspect, um, some of the logic isn't necessarily clear. So with like a vector type, vector is just like a container for multiple types. So you have your generic types, your type T, vector type T. It's going to hold all of these generic types. The inheritance of that send sync, well, if the vector only contains objects that are going to have that trait, so if the T type, the generic type, has that trait, then the whole vector can inherit it. Pretty simple. That's less visible or less it's a little bit more complex when you come to some like the mapped mutex guard where it's now inheriting like two different types. I think they use like T and U type in there. Well, I mean, you can use whatever letters. That's not what's important, but there are two different generic types being used there. And what ended up happening in that, which is part of the standard library for futures, the futures library, what they end up doing there was they only inherited the trait was only bound by one of the types and not the other. So that's basically you could have something that wasn't actually thread safe inheriting those thread safe traits. Which is again a really interesting case, and I'm sorry if I didn't explain it super well. I'm not a big Rust user, so some of this, goes over my head. I had to reread it a few times, but I thought that was a really interesting case for where you might actually start seeing vulnerabilities in truth, because there is that complexity there in terms of making sure you do get all of your thread safety in place, basically.
Yeah, I mean, it's really weird. Like, even if you do use Rust, like, this is kind of the nitty gritty details of how Rust provides those memory guarantees. Like, so I think even if you like wrote Rust often or whatever, like, it's hard to cover this. Like, this paper broke my brain. I'm not gonna lie. Like, you covered this a lot better than I would have been able to, because it's just talking about a lot of nuances in the, I guess, the Rust engine or the Rust design, that I'm just not familiar with. So yeah, I mean, these are really like low level like bugs. If you are interested in reading the paper, like they do go really deep into like how these memory safe guarantees are happening and how these patterns work and some examples. But um, I think you will have to kind of struggle through it to really appreciate it, because this is one of the tougher papers that we've covered, I think.
Yeah, or you just need to be more familiar with Rust and their type system and all of this. I mean, that's the other part of it.
Yeah,
Just lack of familiarity on my part, which I'll completely admit makes me somewhat unprepared to cover this well. But
but
I
it
think
is
I
really
kind of get
interesting.
it. Yeah.
Y-
And I mean, it's interesting just to see that research coming out. I mean, I know that's not necessarily the focus of this paper being to document the vulnerabilities, but that is something I'd like to see, that there is that research going on into what are the security issues for Rust. Um, because I mean, that matters, especially as we have been seeing more Rust adoption the past several years.
there's been a push to move code towards Rust, especially in like really security sensitive areas,
Yeah, make
like
everything Rust.
yeah, but like critical components that are accessible to like sandboxes and stuff like that. There's a big interest of moving towards Rust for at least some of those, to try to provide some more guarantees and sandboxes. But yeah, I mean, the main reason I liked these patterns and these types of issues they call out, even though I don't fully understand or appreciate all the nuances of them, is they're bugs that it's like like it's really hard to think about. It's not something you think about. Um, it's easy to just write Rust and think, okay, I'm fine. I'm using, a library and all the code I'm writing is safe. But if that library happens to be doing unsafe stuff, which is somewhat common from what I've seen, then it doesn't necessarily mean your application is safe. Even if the code that you write, like even if you don't write any unsafe code in your application, if you're using a library that has one of these issues, I mean, the meme of being completely secure for using Rust kind of, falls apart there. So
Yeah,
it's
but
really cool.
like I said at the outset, all that unsafe code is some that gets the extra scrutiny because you do have a bit of trust in everything else.
Exactly.
Like there's huge benefit to that also. I don't want to sit here and shill Rust because, like I said, I'm not even using it. I do think there are benefits to learning it. I don't know. I'll pretty much repeat this anytime we talk about Rust. I still think, like, as much as I want Rust to actually get used, I feel like, we're going to see these concepts that Rust has kind of spearheaded and trail broke on adopted by other languages, which will get more popular. I feel like just using Rust, it just feels like such a pain to actually use, and like the kind of productivity as a developer with it.
I hate the
It isn't
syntax of
that
it.
great. Yeah,
I hate it.
syntax you can. Yeah, I mean, you can get over syntax, I think, but oh yeah, I mean, I really appreciate the research in this area, though. I mean, it's valuable information to have, and just to have it out there, it's like, yeah, these are issues in Rust that you need to be aware of.
Yeah. Yeah, I mean, I kind of have the same philosophy on Rust. Like, I like what it tries to do. I like the concepts it has. I just don't like writing it. I've tried multiple times to like get into Rust and try to, enjoy writing it. And I'm like, when I'm writing, I'm just like, this sucks. I could write this so much faster in something else. Um, So yeah, I mean that's my problem with Rust. But anyway, getting back to the paper a little bit, they after detailing those patterns, they do go on to talk about their tool called Rudra, which uses heuristics to find these issues they listed, with the goal in mind of keeping generic type awareness, making sure it stays scalable and easy to use for package developers, and allowing adjustable precision for dealing with false positive rates and whatnot. They talk about two algorithms they use, which I won't go into detail on them, but the two algorithms there are the unsafe data flow checker for looking for the first two patterns, with panic safety and higher order safety invariants, and they have a send sync variance checker for the send and sync trait issues. Like I said, they go into a good bit of detail on those algorithms and how they model object lifetimes and stuff. But we're not going to cover that here because it gets pretty complex, and you kind of have to understand a lot of the nuances with the Rust type system to fully appreciate it. And a lot of it went over my head, to be honest. Their tool was used though to find 264 previously unknown memory safety issues in 145 different packages, and that resulted in 76 CDEs. So, I mean, their tool has obviously been very effective in trying to find issues in the Rust ecosystem. So, I thought that was worth calling out. Um, But yeah, I think the thing that both of us thought was more interesting out of the paper was just the patterns themselves, and not so much the tool. That said, their tool is open source on GitHub for anyone who wants to check it out or use it. Um, they kind of link to that in the paper. They also have some of their POCs for the vulnerabilities they detail. They have repositories for that. So, if you're interested in that, you can check it out and dig through the source code of the tool. But yeah, we're mostly going to glance over it with this paper because the patterns are ultimately like what we wanted to call out here. But yeah, unless you have anything else you wanted to add on that paper, Z, I think we'll go ahead and wrap it up.
I guess I can end with, everybody should use Rust for everything.
Yes, this is now the Rust Shill podcast. We're going to be changing our logo to Ferris. It's coming. Don't worry. But yeah, with all that said, that's where we're going to end the show for this week. Thank you to everyone who tuned in. The VOD will be up on Twitch immediately or on YouTube at 6 p.m. Eastern tomorrow. We also have previous podcasts up on Spotify, Apple Podcasts, and some other platforms through Anchor. For alerts of when we're going live and to join the community, follow us on Twitter and join our Discord. I'll put the Discord in chat for anyone who wants to join there. But yeah, we'll be back next Monday at 3 p.m. Eastern, 12 p.m. Pacific for the Bounty episode, and next Tuesday at 7 p.m. Eastern, 4 p.m. Pacific for the binary stuff. And we'll see you all then. Take care.